Okay, so we're very happy to have Daniel Ranard from MIT. He's going to give us a bit of a sort of understanding of what coarse-grained entropy means. Okay, thanks, Dan.
Okay. So I'm going to be talking about coarse-grained entropy as counting microstates. And hopefully I chose this topic because I was hoping it would be interesting no matter what sort of theorist you are, what sort of quantum systems you think about. The technical core of the result will be using quantum information theory, but I know that we're not mainly quantum information theorists here, so I'll just prove the simplest version of this in what I hope is a very pedagogical way, so hopefully you'll understand the main ideas here. So I'll start with background, talking about what I'm calling coarse-grained entropy, and that's SCG, the coarse-grained entropy. And then the main result, I'll explain this equation in a few minutes, but it's the main result. The punchline is that the coarse-grained entropy is counting the log of the number of so-called microstates. I'll also explain what that means, and then I'll go into this proof of the simplest case of the theorem. So the setup or motivation is that I'll be imagining some lattice Hilbert space. Here's my lattice. And just as motivation, imagine some local lattice Hamiltonian. And we have some state evolving. And now we can ask, what is the entropy of this system? So how can we define the entropy in this quantum setting? There's lots of ways to define entropy. There's lots of definitions depending on what your ultimate goal is. But let's say we want to make an analogy to classical physics, where we have the second law of thermodynamics and we have some entropy that increases over time. So what entropy do we want to use? Well, the most naive thing that you might have tried to do is you say, first you recall that there's this so-called Shannon entropy for a probability distribution. If you have a probability distribution pi with weights pi that sum to 1, you define this Shannon entropy. And then in quantum mechanics, you often define this analogous von Neumann entropy. Which is just like the Shannon entropy of the eigenvalues of the density matrix rho. So now the most naive possible thing you could have tried to do in this situation where we wanted to find an entropy for our many-body system is you might have tried to say, well, here this is our state evolving in time. So you could just try to calculate the von Neumann entropy. Now, of course, in this case, it's going to be 0 because we have some pure state, and this formula just gives 0, which is to say the probability distribution over eigenstates is concentrated, so there's 0 entropy. So this, of course, is not a good analog of the classical entropy in the sense of something that increases under the second law. And this is a familiar observation to many of you, I'm sure.
I have a question.
Yep.
If you're just evolving the state and it's sitting by itself, it's not interacting with the environment, why should you get a second law? Like,
sure, so I'm not trying to say this is any great paradox or something, but what you might have wanted is if you have a closed quantum system that's evolving in time, if the system is in fact, a gas of particles that's getting mixed up and thermalizing or something, even if there's no separate environment, you might have wanted a notion of entropy that does increase. It's not a paradox that this definition doesn't work for that, but just a desideratum you might have had is I would like a definition of entropy that, analogous to the classical one, increases even for a closed system.
I see, okay.
So, this definition is too naive to work as a definition like the one I just said. So if you go back to the classical case, this isn't really a paradox or anything, and you see the exact same situation even in classical physics. So if I had some classical phase space with these phase space coordinates, then maybe the state at time 0 is just some particular microstate that's evolving under some Hamiltonian evolution. And now if you tried to define entropy of this classical system in the following way, you could have said, look, let's pretend I have a classical probability distribution I'll also call rho as a probability distribution over the phase space coordinates. And now I might have tried to define S like integral. Oh, I realize I'm not writing bigger like I promised I would, but now I'll start writing bigger. So you might have tried to define a classical entropy of this in this classical situation like this, but this entropy is also constant in time, just like in the quantum case. That's actually just a consequence of Liouville's theorem. So again, this is just telling you that the right notion of entropy that increases under the second law is not this naive one that just counts the entropy of the probability distribution, because that entropy does not change in time. So what is the notion of entropy that does change in time? Well, sometimes to distinguish it from this more naive definition, people call this the coarse-grained entropy. So first I'll just remind you what this would be classically. So you have some microstate of your system, alpha, but then to calculate the coarse-grained entropy or the Boltzmann entropy, you ask, what is the number of other microstates that I'll call alpha prime with the same coarse-grained properties. And now you get to choose what you mean by your coarse graining, but often we mean, for instance, the same total energy or the same total volume. It depends on your system. And then, as we know, you would define the entropy as log of the number of other microstates that have those same coarse-grained properties. So this is just standard statistical mechanics that I'm setting up so that I can draw an analogy in the quantum case. Any questions on this basic setup? Hopefully this isn't revolutionary, but hope maybe my definitions make sense. So this is all just sort of motivation. Oh, yeah.
Yes. What sort of metric are you using on the microstates to say that they're like close to each other, or?
Oh, sure. So,
or you're saying that like it's some delta function as long as some fixed properties?
yes. So in classical mechanics, in classical statistical mechanics, often you have a continuum of possible microstates that you sort of naively discretize by H bar blobs or something. Or maybe you're working with a system that has discrete configuration space so that in fact there's a discrete number of microstates. So let's imagine we're in that setting for a second. And then this is just counting the number of the finite number of other microstates that have the same properties as your original microstate, like that have the same total energy or something.
Yeah. Okay, and when you go to the continuum, you would use like some relevant length scale to define your metric, I guess.
That's right. That's right. Okay, so now let me talk about the quantum coarse-grained entropy. There's lots of different things that people might want to call the quantum coarse-grained entropy or have defined in the past. I'm going to be using a particularly simple definition that's sort of easy to work with. It has the right general properties, and I first saw it when I was reading Lenny Suskind's black hole, half pop sci, half not pop sci book my first year of graduate school. So this is what he called the coarse-grained entropy. This is what stuck in my mind. So here's how it's defined. You take your lattice, and first you'll need to choose a partition of the lattice into medium-sized chunks. And I'll call these regions A1, A2, A3, up to some AN. So think of these as just a partitioning of your CMT type lattice system. You choose this partition, and then you define the coarse-grained entropy as the sum of the ordinary von Neumann entropies on each region. So this is just the von Neumann entropy of the reduced density matrix of our state psi onto each region. So why would you call this the coarse-grained entropy? Why do you care about it? So let's just talk about some properties. Well, the first property is that if your state is a product state, then the coarse-grained entropy is 0. Now, what about if, on the other hand, we have a state psi of t evolving in time under some local Hamiltonian, and now we want to ask what is the coarse-grained entropy of psi of t? Well, if we wait long enough that the state has locally thermalized, then sort of by definition what that means is that if we trace out everything except some region AI, what it means for the state to have locally thermalized is basically that the reduced density matrix on some region looks like the thermal density matrix for some temperature on that region. So that means that up to some boundary terms, the coarse-grained entropy of this state will look like the sum over regions of so it looks approximately like the entropy of the global thermal state of the Hamiltonian, which is, so that's the sort of the motivating property of this definition of coarse-grained entropy. If you start in some product state, like you imagine a quench or something, even though your system might start out with 0 entropy in this sense of coarse-grained entropy, over time, as you build up entanglement and as each of the regions becomes, its reduced density matrix becomes mixed and gains entropy, then at late times, the coarse-grained entropy just gives you the thermal entropy, which is, the entropy of this density matrix e to the negative beta h. It gives you the global thermal entropy plus some subleading boundary terms. But the extensive part of it is just this classical entropy. So if I plot it over time, it'll start out at 0, and then it'll go up, and then it'll saturate at whatever this classical entropy value is.
Why does it monotonically go up?
So for a given system, it might not monotonically go up. It's sort of a statistical empirical fact that it tends to go up. Sort of like in the classical entropy case, the classical entropy will go up. So I guess the first part of the answer is it doesn't always go up, but it usually does. It depends on the system and the initial state. And then why does it go up usually? Well, basically because the intuition is basically the same as in the classical case where, how should I say? Well, in the quantum case, the entanglement is building up between different regions. So even though it starts out as a product state, as it becomes more entangled, these reduced density matrices now become mixed, and then you have entanglement that's growing. In specific toy models, you can give like a quasi-particle picture to why this happens. Yeah, I don't know if that answers your question.
Not really. I mean, in the classical case, we have things like the Boltzmann equation and things like that. We can prove results like the H theorem for a pretty good understanding of when entropy increases. We don't just have to resort to saying we made a plot for some toy systems.
Yeah, so, yeah, good question.
Can we just say that?
I can list some different, so if this system were a quantized or a quantized classical system and you're on a small h bar limit, then you could upgrade, you could take your classical argument and make a semi-classical argument over here telling you that this entropy was increasing. If this were just like a sort of spin chain or something that didn't necessarily have a nice classical limit, then the arguments people make there are heuristic, but they make analogies to random quantum circuits. That's sort of our best toy model in that case. In the case that you're in a lattice model that looks like a dilute gas of quasi-particles, there's a quasi-particle picture that is sort of like the H theorem picture. That's another analogy, but in general, we don't have any tight general argument.
Should that be some kind of dependence on the size of this region's AI?
Great, so
and presumably the statement that entropy has to always increase should be possible to prove, or even should only be possible to prove in the limit when the number of these regions AI tends to infinity.
yeah, great comment.
Is it
So
possible to prove some kind of statement like this, that in that limit, universally independent of what system you consider, this entropy, coarse-grained entropy has to increase?
yeah, good comment. So first of all, this definition just manifestly depends on the partition that you choose. So that's, in a sense, not very nice. But for states, but you'll find that for a natural setup, if the system is locally equilibrated, you'll get this answer basically as long as the regions are larger than the thermal correlation length. So it's roughly insensitive to exactly how large you choose these regions to be. Now you're asking, can you actually prove this? Again, the quick answer is no, you can't. I don't want to dwell on this too long because if anything, my talk is going to be about giving some more quantitative sense to this. I'm not trying to claim that this always goes up or that I can prove this. I'm just introducing this commonly used definition. A reason that it's hard to just prove a general statement like this is because it's unclear what the true statement to prove is. There's this paradox that happens classically also where if you take a state and you let it evolve for some time, and now you take your same Hamiltonian but time reverse it, or you take your state and you time reverse it, and now you run the evolution again, the entropy is just going to go back down. So somehow the only, right, like if you have a gas of particles that's equilibrating, and then you suddenly switch the Hamiltonian to go backwards, the entropy will decrease again. So these statements, if you're going to prove them, always need to be proven with respect to some measure on initial states or something, and it's difficult. Did that answer your question?
Yes, yeah. Well, usually the way that reversibility works is that in order to reverse the system, you need to set the initial condition. And the entropy means that you basically do not have enough information to do that. Right? The entropy is a deficit of information. And the information you are missing is as I understand, is the entanglement between different regions AI. And if you don't get it right, then presumably you don't have the reversibility, right? Something like this. But it answers my question.
Yeah, and I think your comment makes sense, and yeah, it's a good segue. So the point of my talk, this has just been the motivation. So now that we have this quantum coarse-grained entropy, you might ask, how can we interpret it? What is it the ignorance of? That's sort of what you were just commenting on. And in particular, I want to ask, can we imagine it as a count of the number of microstates in some sense? So I want to take this coarse-grained entropy and ask, is it the log of the number of microstates, and what would that mean? What are the microstates? So that is the point of this talk. And in particular, what I'll try to show is that this definition for coarse-grained entropy on the right, I then derive a formula like this, that it is actually the log of some number m of microstates. Now I'll explain what I mean by those microstates.
Daniel, a question. Can you, so you define like what the area, like AIs have to be bigger than? What is the upper bound? Because you can't take the entire system, right? Like what's the AI has to be much greater than the thermal correlation length, but it has to be much less than question mark.
Sure. So the definition you can just use no matter what the AIs are, but you were asking maybe,
Yeah, I mean,
what's the condition on the AI such that this would have held at late times?
Yes.
And the answer is larger than the thermal correlation length, but smaller than basically the light cone speed times the time that the system has been thermalizing.
Okay.
So it should be, the region size should be roughly between beta and VT, where V is like the Lieb-Robinson speed or something. Great. What's the best way to do these chalkboards? Right in the shadow.
There should be one behind that that you can pull down. No, the other way.
Yeah, fine. Yeah, I'll push that up.
Push that all the way up.
Grab the line from the line comes down. Control tab and change the.
That's it, thank you. Yeah, that's right. So what do I mean by microstates in this context? What I'll mean is some pure state phi that has the same coarse-grained properties as the original state. So what do I mean by that? I mean that when I look at the reduced density matrix of phi onto some region AI, this is bar, meaning the complement of AI. So this is the reduced density matrix on AI. I want to get so these are states phi that have the same local reduced density matrices as my original state psi. So that's what I mean by these are other states the system could be in that have the same local properties. And I want to count how many such states there are. The sort of physical interpretation is you have some pure state, it's been evolving for a while, and if you only had access to local measurements, then for all you know, the state could actually be one of these other states phi that have the same local properties. So I'm sort of counting how many other states have the same local properties as my original state. And that count is going to be, the log of that is going to give the coarse-grained entropy. So that will be the function.
Just a naive question. So linear combinations of these guys still satisfy that property, or?
Not necessarily, because if you took like a classical mixture of two of these states, then they would still satisfy this property. But if you took a linear superposition,
Yeah.
then because of cross terms when you take the partial
Right.
trace, or because of interference, so to speak, they might not satisfy this property.
But so when you're counting, so here you're.
Good, so what do I mean by
There's some
counting the
basis,
number of
yeah, yeah,
states? Yeah, good. So great, that's what I'm about to write. So my big M will be the I'll call that star. So find an orthogonal set of these pure states phi that satisfy this equation. And there might be multiple sets, but now take the maximum number of orthogonal states you can find that satisfy this equation. And that's what I'm calling the number of these microstates. So orthogonal states that have the same local properties as your original state.
Is there a reason why you are restricting yourself to pure states phi? You could just start with some density matrix, right? That agrees with all of those things, or is there some condition that guarantees that if you agree with the density matrix from pure state, then you have to be a pure state?
So to the second question, no, there could be a mixed state that agrees
okay.
with the density matrices
Then
of the pure
why-
state. Why am I requiring that these be pure?
Yes.
One sort of silly answer is that with this definition, you'll get coarse-grained entropy equals log m. But maybe why is that an okay definition? So mixed states are already sort of like a probability distribution over pure states.
Yes.
So I want to think of a microstate as a pure state because it's something that's not already a mixture of something else.
So maybe
I mean-
one explanation is make mixed states can be always purified in a larger system.
Yeah, but like the purification would be in a larger Hilbert space. Yeah, which is not necessarily like more like if you were to do that, you would have to replace M by like the dimensionality of the space on which the density matrix is lived, right? But if you purify, like my question is, let's say I have a smaller Hilbert space on which my density matrix is lived, but if I were to like purify those ones, then I could end up with a bigger Hilbert space. So like this doesn't seem like an invariant definition under whether you discuss pure or like if I take a density matrix, I can always write it as sum of pure
Right,
pure states, but that pure states could be live in a larger Hilbert space than the.
I mean, it's different to write a density matrix as a mixture of pure states versus as a partial trace of a pure state on a larger Hilbert space.
Yes. So you're using the PI of pure states to use. Right. Okay.
I have one question. Oh.
Yeah, please.
Yeah, usually, so what are we associating this entropy to? Because usually this looks like it's it scales with the volume of a bar, while usually we associate an entropy to something that scales with the volume of A itself. Like in your top right, over there, it like the maximal value is something like the volume of A times some number. But over here, when we're counting microstates, the number of pure states satisfying this scales like exponentially with the size of A bar.
This is for all I.
So, yeah, good. So the first, your question is still valid, but first just to make sure we're on the same page, I'm requiring that this is true for all I. So I want the so-called microstate to have the same reduced density matrix on every region.
Oh, I missed that. Okay.
But you are right that n will end up being exponential in the volume of the region. But then what the log, which is then going to be extensive, is going to be like this coarse-grained entropy. And this is what I'll be trying to show. And just to see why both of them are extensive, well, the coarse-grained entropy, it was the sum over all regions of some entropy on a region. So that will be extensive. And then because n will end up being exponential in system size, this is also extensive.
Okay, so this is a definition of entropy for the total system, not for subsystems.
Right. It's like, yeah, you sum over subsystems.
Okay, thank you.
So I want to try to spend the bulk of my remaining time sketching at least a proof of the simplest case of this equality. So this boxed equation is going to be the thing I'm trying to prove. The definition of n is given here. Please ask if there's any more ambiguity there. And then the definition of the coarse-grained entropy is just going to be what's given here. And what I'm trying to prove is independent of any Hamiltonian. It's sort of like a kinematical fact. I'm just proving a fact about states. So whether or not you believe that this was monotonic exactly, I mean, that's a separate dynamical fact that's independent from what I'm now going to be talking about. So before I was talking about a lattice and then dividing it up into regions, I now want to think of each of those regions I'm just going to call each of those regions some d-dimensional qubit. D might be very large if I drew my regions large, and that's okay. And then I'm going to have n different regions. So I'm just forgetting their internal structure for a second and thinking of them as just some large finite dimensional Hilbert space on each region. And in particular, for my special case, I'm going to take d equals 2. This is just for simplicity of explaining now. So now it's really as if each region is just a single qubit, but already there's something non-trivial to prove there. And then as a further simplifying fact, let me assume about my psi that the reduced density matrix on each qubit is going to be the same, just some rho 1. And now what is this density matrix going to be? Well, without loss of generality, I can write it in a basis like this. P and Q are just some probabilities. So now this is a simple case where we have the same reduced density matrix on every qubit. And it's just this reduced density matrix here. Okay, and now I'm going to try to prove this fact just in this simple setting. I feel the urge now to be like kneeling. I don't know if that's the right way to do this chapter.
You can pull the board upwards.
This is the right way. There we go. If you have a question, feel free to interrupt.
Does the psi I, or that rho I equals some fixed rho, does that imply that the original state is translationally invariant?
No.
No, it does not.
Yeah. translational invariance would be sufficient, but you could manage to create a state like this that was entangled in some not translation invariant way, and yet the reduced density matrices were still all the same.
So here, you already said this, but you're specializing to some state, just as a warm-up, or?
Yep.
Okay.
Some state that satisfies that.
Yeah, okay.
relevant condition.
It's not even a warm-up because it's all I'm gonna talk about, but yeah. The general theorem is, maybe I'll just mention before I go into the special case more. The state doesn't need to be translation invariant. It doesn't really matter how big these local Hilbert spaces are, although I do need to assume they're finite. And I even have a generalization where you request that the microstates match not just on this partition, but on all partitions of some length scale. But those are generalizations I'm not going to talk about.
Can I ask a question about the subleading term? Just want to anticipate your result. Subleading in what sense? Is it large n?
Yeah.
Correct guess?
I just mean subextensive, so there is actually a root volume correction.
I see. Thank you.
But if you made everything intensive, then the error would be going to 0 as you took the large volume one.
Mm-hmm. Thanks.
Good, so I think I have enough time to do this proof sketch. It's gonna involve some elementary information theory, and I'm going to go through that elementary information theory because I think it's interesting and I don't think everyone here will be familiar with it in advance. So as a brief diversion, but it'll quickly be related, consider random sequences of n bits. I'm gonna tell you this fact about sequences of bits and then relate it back. So sequences of n bits, and I say they're random, the way that we're gonna define this distribution is just that each bit will be independent using these probabilities p and q of getting a 0 and a 1. And now let's just analyze this distribution of bit strings for a second. So
Put the bottom one up and the top one down.
great. Let's just talk about some basic facts about this distribution on bit strings. So on the x-axis, I'll pretend that I've listed all of my bit strings, sort of arbitrarily laid out on the x-axis. These are all the n-bit strings, and there's 2 to the n of them. And now if I choose this p to be a half, then the distribution over bit strings that I get from this will just be the uniform distribution over bit strings, each with probability 1/2 to the n. So let me just draw that. So for p equals half, this is the distribution over bit strings. If on the other hand I took p equal to 1, then I would get this very spiked distribution over bit strings. And in general, the choice of p will control how concentrated this distribution over bit strings is. So in particular, I could write out the probability of any particular bit string, like some bit string like this. What is the probability that I generate that using this procedure? This is like a bunch of random coin flips. Well, the probability is p raised to the number of zeros in the sequence times q raised to the number of ones in the sequence, just for these Bernoulli random variables. And now I can ask, for a typical sequence that I generate in this way, what is the number of zeros and number of ones? Well, so usually the number of zeros is like Pn, and the number of ones is like Qn. So usually this is just equal to P to the Pn plus some error term and Q to the Qn. So the typical strings that I generate, if I ask what was the probability of generating that particular string, it's usually just going to be given by this formula. And now, so let's say I took P to be 1/3 or something. So then this distribution, it's not going to be uniform, but it's going to be clustered on certain strings. Maybe they're not all contiguous on the x-axis, but this is just some sort of silly x-axis. And they'll be roughly clustered on these strings. The total probability of this hump will be 1. The height of this hump, well, most strings, what is their probability? It's this probability here, P to the Pn, Q to the Qn. So that allows us to estimate the number of strings on which this probability distribution is concentrated, just by saying that 1 should be about the number of strings on which the probability distribution is concentrated times P to the Pn, Q to the Qn. So in particular, log of the number of strings on which the distribution is concentrated will be like n times, and then keep this here. Okay, so this is the punchline of that little lesson that we took as a diversion. So what is this telling you? This is sort of just a little lesson about how entropy works. So if we take a bunch of coin flips with a weighted coin that has PQ probabilities, then we get a bunch of different n-bit strings. And the distribution is not uniform if P is not a half, but it's in fact concentrated over some set of typical strings. And you can ask, well, how many strings is this set of coin flips concentrated on? And the answer is that the log of the number of strings it's concentrated on is just n times the entropy of this probability distribution. And we hand wave the epsilons, but we derived that by just calculating the probability of this hump. Anyone want to ask anything there?
Sorry, when you say that one approximate the number of strings times the average probability?
Like what's going on there? Is it?
This is not like overstating, like wouldn't.
It's not what, say again?
Like
overestimating? Is that,
yeah, exactly.
So there is some, I'm leaving out some epsilons, but this is roughly true in the large n limit. I'll say it slightly differently. So if you use this weighted coin and generate a sequence of n flips, then with really high probability, the number of zeros and ones are going to be roughly Pn and Qn plus 1 over root n corrections.
Yeah, that's true.
So that's with really high, so that's the really large probability. That's like 1.
Yeah,
with really large probability, if I count the number of strings that have this typical frequency setup times the probability of those individual strings, then I should get 1. So now I can estimate what is the number of strings with that the probability distribution is concentrated on. So it's these sorts of typical strings that the distribution is concentrated on. How many are there? Yeah, so you can think of entropy as counting this volume on which this distribution is concentrated.
Got another like 15, 20 minutes. We start late.
Yeah, I think that's perfect amount of time. Okay, so where does this leave us with what we were actually trying to prove? So far, I've just talked to you about random bit strings, but now let's relate this back to this question of counting microstates. So the task So the task still is that we want to try to build m different orthogonal microstates that have the right reduced density matrices, and we want to build this many of them. And in this particular special case setup, what is the coarse-grained entropy? Well, it's just the sum of the entropies of each of the reduced density matrices, but they're each the same. So it's just going to be n times s of this probability distribution. Now, things might look sort of promising because we already saw that the number of typical strings, or the log of the number, is already n times this s, which is the same number appearing over here. But what we need to do is actually build microstates. So if I naively took, say, some particular bit string, and I tried to say that that was my microstate, well, that doesn't work, because remember, the microstates need to have the same reduced density matrices as psi, but psi is not just doesn't have pure reduced density matrices on every qubit necessarily. So instead, what we do So what we're going to do is we're going to randomly generate some bit sequences according to this probability distribution, where we weighted each bit by p and q. And we're going to take, say, k, I'll call it for now, of these different bit strings, and we're going to add them up. And now the claim is that this will be a microstate in the sense that we talked about before, because when I trace out all but the ith qubit, this will be approximately rho I, which remember was the same for every qubit in this simple example. Thanks.
What's in the squiggles?
I put too many squiggles on the
No, I
board. Which
just mean
squiggles?
the bottom line. You said it's approximately rho I.
Oh, great. So, plus an error term that I'll now explain. So why is it approximately rho I? Well, let me back up and say I'm about to use a random protocol, a probabilistic construction to construct this state phi. I'll talk about why that's okay in a second, because in the end I want an existence proof. I don't want to use some randomness. But for now I'm just going to be using randomness to construct this state phi. The protocol is I sample each of these bit strings from that distribution. And now what happens when I compute the reduced density matrix? Well, because these are from that distribution, the number of there's going to be about pk strings here that have a 0 in the first slot. And there's going to be about q times k strings here that have a 1 in the first slot. So when I compute the partial trace, I'm going to get about a p and a q here, plus an error term that comes from the fact that the exact frequency of zeros and ones in these randomly chosen strings is not going to be exactly p and q, because it's like calculating an average of k things. I'm not going to get exactly p and q, so there's going to be a root 1 over n correction that comes from, that's the usual root mean square correction when I say I have 100 coin flips and it's a 1/3, 2/3 coin. Do I get 33 heads? Well, not quite. I get 33 plus or minus root 100.
It's k.
What's root 1 over root k, you mean?
Oh, thank you.
And you consider this state to be close enough to be called a microstate.
Oh, good. So
I mean, up here you had an equal.
my star has an equal sign.
Yeah.
Great. Good catch. And what I'm building here are states that are only approximately microstates. That's right. In the next 5 minutes as I finish sketching this, I'm only going to be able to build approximate microstates for you. But in fact, there is a way of sort of bootstrapping those into exact microstates. So in the end, I am proving the thing that I claim with an equal sign. But in this little argument, they're only going to be approximate microstates.
They're exact
They're
in the
exact?
thermodynamic limits, maybe? Not in
Well, it's not that
And
these
are they exact? Yeah, are they exact at finite n?
in what I have proven, they are exact at finite n. You might be wondering, how do I do that, since this method seems to only be getting me approximate microstates. And the way that I'll end up doing it, so I didn't finish explaining this method, but it is true, it'll only get me approximate microstates. And now let me just jump ahead and answer for you, how do I bootstrap those into exact solutions to the equation star? And roughly the way I do it is, if this is the space of reduced density matrices, and I'm trying to, what I want to do is get a state that exactly is at this point that satisfies star, and then my approximate method will always have some random error and get me points that are not quite satisfying star. Then very heuristically, the method that I use to bootstrap the approximate solution to an exact solution is, instead of trying to solve star exactly, I take equations that are nearby and use the same method to try to solve those exactly. So I now get, instead of targeting the original point, I target some nearby points. There's some randomness, so I miss the target by a little bit, and then I triangulate and go back to the exact solution. That's just words I know, but it's evocative.
I'm having a hard time visualizing the solutions. This is some kind of set of quadratic equations that we're intersecting over I inside the vector space.
Quadratic in the components of psi, that's right.
But so the solution set is not a vector space. So why?
That's right, and I'm counting the maximum number of orthogonal solutions I can get. So there is some solution set.
But
And
you
then I
can't
can ask-
take linear combinations of the solutions to make
You
solutions.
said you can't.
You cannot, yeah.
That's
So why why do you only count the orthogonal ones? Why don't you just, like, what is the dimension of the space, for instance?
Well, as you just said, it's not linearly closed, so what do you mean by dimension?
Well, it's a submanifold of a vector space. So is it a finite set? Is it an infinite set?
It's an infinite set, or you're right, it is locally looks like a submanifold in most places. Its dimension is exponentially large. You're right, it is some weird submanifold in the Hilbert space, or most places it looks like.
It's like a curved submanifold, so why are we counting orthogonal states? I don't quite, it seems geometrically unnatural.
I agree it's geometrically unnatural, like if you just gave a mathematician that equation and said count solutions, and by the way, what I mean is orthogonal solutions in the Hilbert space, I agree that's unnatural. I was hoping to convey that it's sort of natural from the physical perspective where, how should I say it? So what's special about orthogonal states in the Hilbert space, a set of orthogonal states? What's special is that, for instance, you can design a measurement whose outcomes are those different orthogonal states. So let's say that all I told you about my state is its local reduced density matrices, and then I told you, oh, actually, there's many states that are consistent with these local reduced density matrices. And I'm gonna quantify that uncertainty, how many states were consistent with it. Well, if I wanted to now perform a measurement, some global measurement on the system to ask which of these states is it, when I do measurements in quantum mechanics, I use some Hermitian observable with orthogonal eigenvectors, and now the number of different outcomes that I need to put in my measurement to distinguish which state it is this number n.
You can distinguish these states by a global.
Yeah, when states are orthogonal, those are the sets of states that you can use a measurement to ask which one is it.
But M is not related to the dimension of this space.
That's right. Not in any obvious way. Maybe I'll also back up and say this equation star, asking whether there is any solution at all is called the quantum marginal problem. I heard that you all had Isaac came here recently who maybe also mentioned the quantum marginal problem. So in general, there might not be a solution for a state satisfying star. In the regime that I'm working in at large n, it turns out that you're basically guaranteed a solution, like this as an upshot of what I'm doing, say you're guaranteed a solution. And then I'm counting the number of orthogonal ones, which I agree is unnatural in a certain perspective, but natural in another. So I was actually almost done with this sketch here. So I said that if you take k randomly sampled strings like this, then you get an approximate solution to star plus a 1/√k error. But we need.
I have another question. So there's two steps of approximation. One is how close you are to the density matrix on each of the qubits, and there's also the fact that you are only approximately orthogonal, right? These states that you pick randomly are not.
Great.
They have like 1/k orthogonality.
Great. So regarding the second approximation, actually, if k is not exponential in the volume, then most of these strings, when I sample them, will be distinct. Because there's some huge number of strings, I'm sampling, say, an order 1 number of them. So in fact, these strings will be orthogonal, and actually these strings are not themselves, these strings are composing one so-called microstate.
Yeah.
I haven't yet, I'm now gonna say, we want more than one microstate, we want more than one phi. So let's call this phi1 that we built using k strings. Now we want to define phi2. How am I gonna do it? Well, the prescription is gonna be, I'm going to again randomly choose k different strings.
Yep.
as long as 2k is still small compared to the total number of strings, then these will all be orthogonal to these, so these states will be exactly orthogonal with high probability.
Yeah, so this is, that has an exponential error and this has a polynomial error, inverse poly error.
Oh, well, with high probability, this will be exactly orthogonal to this state here.
Exponentially small probability.
Yeah.
Yeah.
So this whole construction, well, let me come back to this in 1 minute.
Sorry, phi 2, what is the difference between phi 2 and phi 1?
Yeah, so these are randomly chosen strings. I chose k of them, and then I'm gonna again choose k random strings for this phi 2. I'm gonna flip my coins again, my weighted coin, to choose new strings.
Yeah.
And with high probability, they'll be distinct from the old strings that I chose. Okay, so how many times can I do this? How many states can I generate here? Yeah, I'll be about 5 minutes, yeah, or less. How many states can I generate here? Well, eventually, if I keep picking strings, so let's say I'm on my nth attempt of trying to pick strings. So what's the probability that these strings are no longer orthogonal to the previous strings? Well, the number of times that I've flipped my coins total, if I'm on my nth state, and each state had k terms in it, then there have been nk previous strings that I've used. And whereas the total number of strings, so let me think 1 second. The total number of strings of these typical strings is approximately there's approximately this many typical strings that I get when I do this coin flipping procedure. So this is the fraction of strings that I've used up. So it's also approximately the probability it's roughly the probability that when I try to generate this next state, I get a sequence that I've already used before and lose the orthogonality condition. So as soon as this becomes order 1, the construction breaks down. But as long as it's small, this probabilistic construction works. And then there's a slight subtlety here, which may be obvious to you, which is when you have a probabilistic construction, where you're ultimately trying to do an existence proof, all you need is that there is a non-zero probability that your construction satisfies certain properties. And then because there's a non-zero probability, that object must exist. So as long as this probability of a repeat draw is less than 1, that means there's some positive probability that the construction works. And as long as there's a positive probability, that means that there is some sequence that must have worked. And that's how you get the existence proof to finally prove this. Okay, that concludes the sketch. So I'll stop now for questions. Thanks.
Can I ask just a basic question about that randomly choose? Are you choosing strings that have P and Q zeros and ones to get, once you trace out, to get that P and Q come out, right? Or are you just randomly choosing?
Yeah, so I'm randomly choosing strings where each bit is independently chosen to have 0 or 1 with probability PQ.
I see.
Although those strings will usually have about P and Q fraction of zeros and ones.
What happens if you force it? Does that reduce your error? Say I'm gonna pick only strings that have P zeros and Q ones instead of independent.
Well,
I guess that's set.
You could try to rewrite a proof like that. It actually gets more complicated because if n is finite, then how do I choose exactly a third of the 100 strings to have zeros, since that's not an integer? So you could try to go that route, but since
You would still get a narrative, the 1 over root k, so it's not much.
So you mentioned that you can do this even with regions that, where it's over all partitions or something? Can you say what, I mean, so does that mean you can prove an existence to the marginal problem, not just for these like, for a single partition, but for?
so the analogous statement that so I can make a statement like this, but where I request that the microstates match on geometric but overlapping regions, so they're still contiguous but maybe overlapping. In that version, I then need to use an approximation here. Or rather, in that version, the microstates, I can no longer get them to be exact solutions to this equation. There's now an error term in that equation. And the reason you might have expected that is that as you probably know, the marginal problem when you request solutions that have specified marginals on overlapping regions is in general like a NP hard intractable problem. So I wouldn't have been able to construct some exact solution in some general case.
Did you give an interpretation of this as the number of times that have to perform an experiment given access to a subregion to be able to distinguish states? Is that correct?
I guess I didn't say number of times, but
The number of independent experiments you would have to perform to
if your experiments were measuring like a binary value, like a binary value, then how many repeated experiments would you need to do to figure out which state you were in? That interpretation holds. Yeah, that's right.
Is that also literally the definition of relative entropy?
You're talking about like the operational definition of relative entropy through hypothesis testing.
Yeah. Also in quant, I mean.
Yep.
That's.
Yes, but the setup's a little different. Like if you just had that's if you just have a single copy of a system, you're not thinking of its internal structure or spatial regions.
You could formulate the problem as like given two pure states and I only have access to some subregion, the relative entropy would tell you how many experiments you would have to do, local experiments you'd have to do to be able to distinguish the global state out of which you took a substate. Seems very similar.
So something, no, I think that's a good point. Something like that might be true. That's a good idea. And then the upshot would be that you would, this formula would end up telling you, it would give you like a third thing to relate here. It would tell you this formula is equal to log m is also equal to the number of times in this operational setting that you need to do an experiment or something.
Wait, I'm a little confused about what Neumann said, because I thought if I really only had access to one of these partitions at a time, and we were doing the exact version of this statement, then there are just multiple pure states that all have the exact same reduced density matrices, and I'd never be able to distinguish them by doing just local measurements on each patch.
Well, relative entropy involves two states.
But just by doing local measurements within each patch, I thought you weren't able to distinguish the global state. Because there's all these different global states that have exactly the same density matrices.
Yeah, it's a global measurement that distinguishes.
Yeah, I sort of thought you had meant counting the number of global measurements that you would need to do to determine the state. But
I heard
maybe I misunderstood.
Well, the statement is about, I mean, if you have global measurements that you can do one measurement and distinguish orthogonal states. So it's not that. It's given access to some subsystem, could you distinguish the two? Maybe.
I think the example that Edward said, just the relative entropy is 0, so it's just infinite.
So yeah, if the reduced density matrices are identical, I guess you'd never be able to tell. So the relative entropy would also be 0 again.
We could talk after, but I think there is a way of formulating something like what you were saying that does make sense, but I'm not sure.
So this expression for the coarse-grained entropy in terms of these microstates, do you think it will be useful to, for example, plot this line that you were showing, studying growth of entanglement, things like that?
So I'm not sure, but it would, I have thought about that. It would be nice if that were true. Like, Clay was asking, why does it go up? And I wasn't giving a great answer. And it would be nice if this counting interpretation allowed you to make some better sort of statistical argument analogous to the classical case. Because, classically, the coarse-grained entropy goes up. There's an easy statistical argument, which is that, of course, you're going to move to a macro state with more microstates on average. And now with this interpretation, you sort of want to say something similar here. You want to say, of course, you're going to move to a part of the Hilbert space that has more volume. So I would like to say something like that, but I'm not sure how. Yep.
So when you wrote log m is approximately s coarse-grained, and then the s of p comma q is like for, if you compute it for a single square. Is that it?
Are you talking about over here?
Yeah.
Yeah, so for a single region or square. So in my simplified version, I was pretending that all of these regions were in fact single qubits labeled by, and then the reduced density matrix is then labeled by a single p and q. And then that's what this entropy is here for a single qubit in this case.
And that equation comes from taking, say, log of this last equation that you had. Like where the probability of that repeat draw failing is order 1. This now gives you the relation between.
Oh I guess that's a good. Maybe I didn't finish the last line of the sketch, which is to say, you solve for m when this is equal to order 1, and you find that it's you find log m is 2 to the n times s of.
Or just s.
You mean ns? Yeah. You lose the 2.
Oh yeah, I took a, sorry, yeah. Thank you. Or I can even just call this S coarse-grained. I guess I didn't need to write that. Yeah, you solve this equation and then that's the final answer.
So can I think of it as just n multiplying, because usually when we think about a quantum system thermalizing, it's if we take a subsystem and take the bipartite entanglement, right? How the rest of the system thermalizes the subsystem.
Yeah, often we just look at a single subsystem's von Neumann entropy. That's right.
Does this?
This is just the sum over all regions of that von Neumann entropy.
Okay.
Or sorry, go on. Maybe that didn't answer your.
I don't what kind of additional information? Because it would still give that kind of slope up and margin, right?
Oh, I don't know if I'm answering your question, but you're right that all the time we consider just the entropy of a single region and then plot its dynamics. And the fact that we're now summing over regions is not supposed to be that different. I mean, it is a natural quantity precisely because it's just the sum over things that we often compute. And then the new part is just to quantifiably give it this microstate interpretation.
I see.
Yeah, this quantity is just when people calculate von Neumann entropies of CMT or QFTs or whatever, this is just the sum of those over different regions.
As a microstate count.
Yeah, and then asking, how do we interpret that as microstates? Cool.
Any last questions for the speaker?
Can you just, the K needs to be big or?
So.
If I use 2, probably will not work.
Yeah, it's a little ambiguous because there's this, what I end up doing is I take K to be order, I think log n or something. So I take K large enough to get some smallish error here. And then the question is, how small do I need to get it for when I bootstrap to my exact solutions? I didn't explain how I do that, so.
good.